je een ander vak ziet, dat er wel posities zijn die natuurlijk eigenlijk nog zelf eigenlijk kan niet meegaan. Maar het maakt niet wel makkelijk.
Hi everyone, good evening. Hope everyone is doing well tonight. We are, tonight is going to be a very exciting class, hopefully, because there's a lot of content and topics we want to cover. So we're kind of like ramping up from this week, hopefully. Before we start, just want to make a couple announcements. As I mentioned before, I'm not going to be available next week, but someone else, her name is Florence Chen. She's going to sub for me, okay? But it's going to be a different classroom. I mean, you will get an email from Continuing Studies. At the end of the class, I'm going to show you the map and where the class is. It's very easy. There's a library right next here. It's called Lath Rope, I think. Do you know? Is that correct? So it's right across here. Yeah, I mean, you will see it. I'll show it to you on the map. So it's class 299, I guess. The same hours, it's going to be like week 4, a new set of slides as well. I sent all the details and all the material to her. I also posted the slides for week 4 since I'm not going to be here, so I mean you can access it from now. And I mean Florence is she took this class I think 2 years ago maybe, and I think that her final project was the best ever. So make sure that you ask about her final project as well. I'm sure she has a lot of ideas for the final project, and make sure that you understand her project because she did some very cool stuff. And right now she's also working as a data scientist. So it would be nice to hear from her, her whole story because she didn't have any background before, and how she went through this whole thing. Okay, and feel free to ask questions and chat with her. I think it should be a pretty informative session. And again, I will be available through email and text. You don't have my number, but through email. And I mean, that's what I told my team. So, but yeah, through email, I will respond. I mean, there's just some time zone difference, but I'll try to get to you as soon as possible if you have any questions about the lab work, about the final projects. All right. And tonight we're going to talk about the final project a little in more details, and just want to make sure that everyone has found a team. We'll do that later. So there's just a few minutes here we have to finish. And then once we get into week 3 slides, we will talk about the final project and also some resources that you can use for finding data sets. All right? Some very cool and interesting data sets. I learned about one of them like 2 days ago and I put it in the slides. It's a very beautiful data set, and we'll talk about it later. Anyway, so we got to another mice project, and we were talking about heat maps here, remember? So we said this Dr. Carmichael's lab at UCLA is the neuroscience department. These folks are targeting to cure brain stroke and help to cure this. These are some numbers in the U.S. Like almost 800,000 strokes in the U.S. happens annually, and 30% of the people get disabled right away, and they never recover. And then 20 to 30% are also taken to nursing home. So when brain stroke happens, many people find disability, but after some time they can recover, right? I mean, their brain starts recovering their disability. So for example, if they cannot move their hand, after a few months they will be able to do so. What these guys want to do is they want to understand the mechanism of the brain to see how it's recovering itself during this process. If they can learn that, they can they can build some drugs that can expedite this process eventually. So they were running a very nice experiment on, again, the poor mice, which first they did they did a surgery on the mice's brain to cause brain stroke, and then they were monitoring its brain map once every week, and then comparing these maps and see what the difference is. So for the brain map means they actually put the mice inside a pretty big device. I don't have the photo here because that was a pretty unique device that it kind of holds the mice, and it shines a laser to different X and Y locations of its brain. And every time some part of its body, you know, is going to have some displacement, right? It's going to move, right? Once the right hand goes up, for the next laser shine, the left leg goes up, and so on and so forth. So there's also lasers all around that capture the displacement of its body. So we have an X and Y for the brain, right? And we also have Z, which is the displacement for every X and Y. And that's why we use a heat map. So just by looking at this, I mean, this is the X and Y of the brain, right? I mean, if you look at it as the brain as like two-dimensional. And then the color is showing the Z dimension. And if it's like closer to 0, which means like no displacement, it means, or no movement, it's dark black, it's black. And if it's like, it has a larger movement, it's going to be closer to white. And I mean, just by looking at this image, you can kind of guess like where the cortex of the brain is. It's probably around this area, right? Because it's causing a lot of displacement and movement. Anyway, just wanted to show you one of the applications of heat map. Wherever you have X and Y coordinations, and then you have another variable for each of those X and Ys, you probably want to create a heat map. Again, there's tons of examples. We also talked about this. Did anyone look into this, Claude Lee? Did anyone do the code here, by any chance? So I'm just going to show you a very quick demo of Claude Lee. I mean, you can get Claude Lee installed and just copy and paste the code to get this plot. I'm going to show you more on their website, which you can explore simply by just going to their website. Oops. It's Plotly, like an R. Plotly is available both in R and in Python. It's free and open source on both. But this is the website, the tutorial for R. And as you can see, like under examples, it's usually under examples or gallery. You can find tons of examples here. And depending on what you want to do, like for example, if you want to do some interactive box plots, you can just click on it. And the great thing about it is that it has some sample code here. Look at it. I mean, this is the code, right? This is the source code. You don't even need the rest of the code. It's only these 2 lines of code in order to create this plot. So you can come up. You can simply create this interactive plot, which, as you can see, if you hover the mouse over the plot, you will see more information and more data. And then you can customize it. You can say like, okay, what variable I want to show, I want to display on the plot once I hover over. You can even like zoom in and zoom out. Well, here we don't have any data points, but like for others, I'm going to show it to you how it works. And the cool thing, as I said, is you see the source code, and then you see the result. You see the plot. You can just copy and paste the same thing in RStudio. So for example, we have dots here and a box plot. You can like zoom in like this, to see the dots in more detail, and then you can double tap and zoom out. There are some neat tools here that you can use for publishing the Plotly, for creating a JPEG, for sharing it with others, and embed it into your website. You can also get the code. Yeah.
So I got an error. It says there's no package called Plotly.
So you need to install it first, right?
I didn't see it in the user live.
See, all you have to do is just go to packages, install Plotly. There we go. So just make sure that it gets installed, and then you can copy and paste the code, and it should work. Oh, so anytime you see this, look at it. Anytime you see this message here, do you want to install from sources the package which needs compilation? Always say no. Okay, always say no. I don't want this. If you say yes, you'll get an error. It's not going to run. The reason you see this error is, or this message is, because the version of the R that you're using is not like the same version that Plotly was developed in. Okay, that's it. But it's okay. It's more like a warning message. It's not a problem. So I'm just going to say no, no, and then it gets it downloaded and installed automatically. Okay. I mean, anytime you get a package installed, do the library of package. Make sure it's running with no errors. If you're getting errors, it means the package was not installed successfully. Okay. Or another common error that you may see is this function does not exist. That means that the library that contains that function was not loaded. or was not installed. Okay. And, all right. Yeah, it's gonna take some time. Yeah, finally done. Just gonna show you more examples. So again, like you can create these box plots. You also have a legend here, and then you can click on the legend to turn them. You know, you can like opt or turn them on and off. If I click on this one, I can take it out. You know, this is very cool. Like for the cases which the plot is very there's like so many data points or so many box plots, and you want to take off some of them, and then take a snapshot and put it in your slides. So. I mean, the first time that I actually used this at work was when I was doing a plot, and then my manager was giving me feedback all the time and telling me that, okay, remove this, put that, add this, add that. I thought of, okay, let's come up with something like this, and then I can share it with my manager, and he can play around and get whatever plot he wants, okay? Especially on week 6 or 7, when we talk about Shiny. Shiny is another package that you can create web apps in R. And that, using that package, and then integrating Plotly into Shiny, you can even create like a web app and UI interface, and the users can explore any type of plots they want with any inputs, with any X and Y's, which we'll see later as well. All right, so another example again, you can like turn it on, you can turn off or take out these categories, for example, in the legend here. As I said, you can zoom in just by like doing that, and then double tap and zooming out. So again, tons of examples. I mean, if I just go back here, some other Plotlys, these are like maps. This is like the US map, and then you hover over every state that will show the population, a lot more information about every state, as you can see in the example. So I don't want to go through each of them right now. 3D plots is also pretty cool. Again, you have the source code here, and then you can see how the plot looks like. This is how it looks like, and then you can even rotate, the plot. You can zoom in, zoom out, again, rotate, like this. All right? And as I said, and look at the code. It's this, only this. It's one line, half a line for creating this 3D plot, okay? It's very useful. I mean, there's many applications for using this tool. And as I said, it's very simple. I mean, even though the visualization and the plot looks pretty sophisticated, but the code is like very straightforward and simple. All right, any questions? Again, you can explore more examples on the Plotly tutorial.
So in that code, where are you telling it the type of, like, where are you saying this is a scatter plot? Kind of like the geom.
I see. I'm not sure. I have to look into the code. So this is the function we use. This is the data set. This is the main variable that you're using for X and Y. And then color, size, character, text.
Does it just default to the scatter plot?
I think, yeah, this is the default, yeah, scatter plot. If you want to change it like to a box plot, I think you have to set up a parameter. I don't know, you have to look up. But, I mean, that's why I'm saying you should never write the code from scratch. I mean, just find an example and then make your changes. Okay, I mean, like, we don't have a box plot here, but we can look into one of those box plots in the gallery, copy and paste it, and then play around with it together plots. And that's what I usually do. Because, but I mean, most of the syntax here is compatible with R. It's not like something very different. But I mean, obviously the syntax in every package is going to be developed by the developer of the package. So it may be different in some cases. Oh, yeah. I mean, I think this is probably the best website to learn Plotly if you want to get into it. I mean, the same website I was looking at, and also the galleries, and also all the examples here. All right. Is there anything else we missed from this week? I think that's it, right? Any questions? Let's get into week 4. 3. All right. Did everyone do the lab work? How many people finished the lab work? All right. Cool. Yeah, I got a few emails, which was great, and it was clear that doing the lab work. Okay, let's talk about the final project very briefly. How many people do not have a team yet for the final project? All right. That's what? Every team?
How many people?
And the team, 3 or 4 people. Okay. Try not to be less and not more. It's okay if we have like one team with 2 people, but try to have teams of 3 or 4 people. So almost everyone, right? Almost everyone. So tonight, your lab work, the task is to find a teammate, okay? Before we start week 5, I will send a reminder, an email. But before we start week 5, which is going to be like exactly 2 weeks from now, okay? Before the class, everyone is supposed to. This is part of the front-end project. To go to Canvas under the discussion section, I'll create a new discussion called Final Projects, and just put your team members, team names, and also the data set that you've picked, that you have selected, okay? Again, you don't necessarily need to stick to the same data set until like week 8. You can change it anytime, but just put like something tentative there. Just want to make sure that you have at least brainstormed once about the data set that you want to work on, okay? Otherwise, usually most people are going to start thinking about it on week 7. So let's do it earlier, all right? And again, if you have any questions, just send me an email. Again, I have 3-4 slides here that will give you some resources for finding a data set. It's not only this, you can find the data set from anywhere. These are just some recommendations. Or especially, I heard from some people that they have their own data set at work, at their company, which they have been using it and they want to apply some data mining tasks on it. Well, that's even preferred. And if you can share that with the whole class, and you don't need to share the actual data, just if you're able to like show the results with plots out of the data set, go ahead and use your own data set. That's obviously preferred. You can also benefit from that. The first link is, this is a link to all of the built-in data sets in R, like the MPG, US arrest, and all those data sets you can find in here. You can find the raw data, you can find a full detailed explanation for every data set. That's one thing. I won't really recommend that, okay, because the data sets are pretty cliche and not big. Some of them are very small, like just 30 rows, similar to MPG, right? It's a pretty small data set for empty cars. This one is the benchmark data set. It's called the Machine Learning Repository at UCI. In almost every machine learning publication, you can find a reference to this website. So if you come up with a model, with an algorithm in machine learning, and you want to show that it's improving and you want to get it published, you probably have to use some of the data sets here to demonstrate the idea and show that it's working, or that you're improving the accuracy, for example. Okay? So this is very well known among the community if you want to use it. This data set here at UCR, it's probably the richest data set for time series data, okay, which I won't recommend for this class because we're not going to, tonight we will talk about time series analysis briefly, like 10 to 15 minutes, but we're not going to get into details. Time series analysis is more complex than analyzing discrete data, which is what we're going to be doing in this class. So you can probably avoid this for now. Okay, just if you want to look at it, just put it here for your information. And this is also some public data set from San Francisco, and some very new, up-to-date data sets you can find about I don't know, a lot of stuff like population of different like cities, areas, traffic information, routes, different routes, and all that. So this is pretty cool if you want to take a look at it. Like last quarter, I think 2 of the projects they selected their data set from this repository here. And finally, Kaggle. Does anyone use Kaggle? Has seen Kaggle? Yeah? No one? You heard about it. So Kaggle was acquired by Google, I think last year, maybe. And this is kind of like one of the richest machine learning repositories for machine learning projects. Many companies post their problem and project here, and also provide some sample data sets to work on. And they ask the whole community to build and train models in order to solve these problems. Okay, and then whichever model gets like the highest accuracy on their test data set will get the prize. And some of these projects, which you can look it up, have like $1 million price for some of them, or like a couple $100,000. You can easily find it. But if one day you become jobless, then you can definitely try this out. Okay, it's I think a good income here. You can look it up. It's, as I said, tons of interesting data sets you can find here. It's just, the website is Kaggle.com. I'm going to show you some examples and where you can get it. Kaggle, there we go. So it's Kaggle.com, and you can, here, there's like competitions, and there's also data sets. If you click on competitions, for example, something that is very interesting about competitions is, if you sort it in order, you can kind of figure out what is the trend in machine learning and data science. What kind of problems companies are trying to attack, or are trying to tackle, right? It will give you a beautiful idea. I mean, just if you have some time and you want to waste some time, maybe just sit down and look at these projects. They're very interesting, some of them. I mean, you can't really believe like if data can really solve this problem with in machine learning. And you can also see the prize amount here. So let's sort it based on prize, because we love money. How else can you sort it? Like, yeah, also based on date as well. And again, you can look into these competitions. They're pretty interesting. Especially, I think after this class, you will definitely be able to participate in these competitions, because we're going to solve very similar problems in the class, maybe in a smaller amount of data, maybe, but very similar. I mean, you have to come up with, like, for example, a predictor, a regression model or classification model that has to classify or predict a target variable, and your model has to have the the highest accuracy. So that's how you get compared with other attendees in the competition. Or you can click on data set. I don't know why it's not loading here. Again, you can see all these data sets here. There are like tons of them. You can even, well, this is like sorted based on hotness. I'm not sure what is hotness here, but you can just click on it. Again, there's like tons of sample data there, complete explanation about all of the columns and all of the features. So as I said, you can definitely look into this. I think it's pretty cool data here. All right. What else do we have here? Oh, this is that I learned recently. It's called Mimic. Has anyone seen this before? Mimic. I mean, I saw it for the first time like 2 days ago. Mimic. It's a health data repository from MIT, from one of the MIT labs, and as they have explained here, it's developed by the MIT lab, and they have a lot of health data associated with 40,000 care patients. It includes demographics, vital signs, laboratory tests, medications, and more. I'm doing another project out of this class, and I need this data, and that's the reason that I'm using this data set right now. I need demographics from different users, and because to do something. And you can look into this. In order to get access, you can go to the website. They have you need to do it like an online training. It's gonna take like maybe 20 minutes. And then you have to sign something and send an email, and then they will give you access to the data. All right? As I said, I'm not really experienced in this one, so I don't really have anything to say. I mean, if you learn something, just let me know and share it with the whole class, please. All right. Now, any questions about the final project? Other than, I mean, the first thing is that we need a team to do the final project, right? And then find your data set. The third step was to import the data into R, which we will see tonight. Import data into R. This is the topic that I want to talk about right now. It's 1 line of code. So by end of tonight, you will be able to complete 3 steps out of 5 steps of your final project. Only in step 5 is just like presentation. So only step 4 is building models, which we will talk about on week 4, 5, and 6. All right. Question? No. It's up to you, yeah. At the beginning, I asked like to see if anyone has a team. Almost no one has joined the team yet. So I think you can, after the class, you can all talk together and find your ideal team based on, I don't know what, So yeah, whatever. All right, and please be nice and kind to each other. Okay, there were some examples I told you, like people, honestly, like last quarter, someone, I think they were like spouses, I think so, the guy, and they were literally like fighting. I mean, here in the class, and I was like acting like a psychologist, you know, and calming them down, and it was very, you know, a tough situation there. But yeah, I mean, I know I'm working as a team. Even like finding a data set that is going to be interesting for all the team members is not easy. Okay, I'm sure you're going to be struggling at that point, but I mean, that's how it works. That's what teamwork is about, and we want to practice this in this class. You have a question?
Yeah. So on the final project, we have some guidelines on you know, what to include, sort of stretch yourself a little on the level right that you want to achieve, and maybe there are different levels.
Yeah.
Sort of just high level, like, hey, make sure you have a data set that meets these criteria in order to.
I mean, yeah. I mean, for this step, I mean, for the first assignment that we have for next week, for 2 weeks from now, all you have to do is just come up with a data set. Even if you don't really know what to do with it, it's okay. But I think the main goal of the project, you will figure it out in classification and regression, which we will start from tonight, some introduction, but mainly starting from next week, we'll get our hands on the code. That's going to be the main thing, you know. So in your data set, you have to find one of the columns, which we call it like a target variable, and try to use the rest of your data to predict that, or to estimate that. I mean, that's going to be the main goal, okay? So finding the target variable is up to you. I mean, it could be anything. Or you can test like multiple target variables and see which one is predictable. Sometimes some of them are not predictable given the information and the features. You'll figure this out. I mean, especially for week 4 and 5, as I said, we're going to do many examples in the class. For example, for next week, we have a data set from house prices. And in the class, we're going to do this. We're going to exercise this project. We want to use all the information there, like the number of bedrooms, the number of baths, square feet, blah, 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 to predict the prices of those houses. And then we can say that, okay, here's the accuracy of our estimation. Yeah. So this could be like a sample project for the final project. Again, I think we will see many examples during the projects and the examples that we have in the class. All right, let's talk about importing data into R, just like this guy. This is a very nice tutorial for importing data into R because depending on the type of data or the format of the data that you want to import in R, there's different functions, right? If it's a CSV, if it's an Excel, if it's an XML file, or if it's a SQL format, there's going to be like different packages, you know, different functions. This is like a complete tutorial that explains all different types of data that exist, okay? Any kind of extensions, any kind of formats, you can find it here. But for now, we're going to talk about one of the most common formats, which is CSV and Excel, okay? And we will do this in the class. We're just going to write some code to import some data into R. All right, let's do this. This is the real estate data set that I was talking about just a minute ago. Please, if you can go to this website, just click on the link and download the real estate CSV file. I'm going to do the same. So I mean, click on it or copy paste the the URL, and then you need to scroll down. So it's not the first one. The first one is a sample insurance portfolio here. We don't need that one. Skip this. And then the second data set is called real estate transactions. If you click on download.csv file, it will download the file automatically. And the name of the file is Sacramento Real Estate Transactions.csv. All right. Oh, I don't have Excel installed here, I guess. I thought I had it. Anyway, I can't open an Excel, but if you guys want to, if you just double click on it, it will open up in Excel and you can see the different columns. Was everyone able to find and locate this file here? again, it's the second data set in this website called Real Estate Transactions. The name of the file is called Sacramento real estate transactions.csv. And just double click on it, open it in Excel, see how the data looks like. What are the columns you see?
Street, city,
Street address, city name.
state,
Uh-huh. Exactly.
Bed,
Number of beds, number of bath,
square feet,
price.
sale date, price,
Exactly. Sale date and zip code, I guess.
latitude,
Latitude, longitude. Did everyone get the data set? Yeah? Everyone? Okay. Okay, let's do this. Let's the name of the file is pretty long. Let's go and, I mean, you don't need to do this, but I'm just gonna do it like real state.csv. I'm just changing the name to a shorter name. I want to write less code for the name of the file. I mean, it doesn't really matter, but just in case. All right, now let's go ahead. So I have the file, which is downloaded and under the downloads folder. Okay, I mean, I think for all Mac users, it's going to be downloaded there automatically, but for Windows, it's probably somewhere else. Now, let's go ahead and import this CSV file into R. Let's see how it works. Okay, so open RStudio. There's two different ways that you can import any data set into R. Number one is here, which I don't usually do this, but I mean, it's up to you. If you like this better, it's maybe easier, but you can't really customize it. I'll show you why. Here under Files, you can go and find the file, or you can also click on this. See, do you see this? The three dots here. Go to Directory. Do you see this? See, I'm pointing to it here. Right? If you click on this, it will just open the, like the Finder, and you can go and like find the, the file here. Example. Well, yeah, here it is, realestate.csv. Well, because I don't have Excel installed here, I think it's like not showing up. But anyway, one way is that you click on it, and then you have like an option of import the data, and then you can click on it, and then a window will open up, and you have to like click next, 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 and you can get it imported. But I'm not going to do this for now. Okay, I'm going to try out something else. Okay, let's go ahead and do this one. We just want to write some script to automatically import the data into R. Okay, now for here, first of all, make sure that you navigate to the folder that, so through this window here, navigate to the folder that contains the data set. So in my example, it's under downloads. So I'm just going to click on downloads here, right? I'm just going to click on downloads, and it goes into downloads, right? And if you click on more, you have an option of set as working directory. If you do this, I'm going to click on this. You can also see the code. I mean, if you wanted to write the code, it would be just set WD is the code for doing this, and then you put the path. You put the path. What happens here is, this is useful sometimes. Once you do this, it means that the compiler knows that it has to look into this directory. So if you say, for example, import realestate.csv, the compiler will automatically only look into downloads, not anywhere else. But if you want to skip this, you can provide the full path to the file. That is also going to work. There's no difference, okay? So you can either set the working directory. I just showed this because it's useful for other applications as well. And then just use the name file to import it. Or you can use the full path to the file to import it, okay? Now for doing this, we are going to use a package called utils. And run it, just make sure it's loading. You don't need to install it because it's pre-installed, right? Did it run for everyone? Was everyone able to load utils? So utils is one of the packages. It's not the only package that you can use for importing CSVs, but it's one of the common ones. And then in utils, there's a function called read.csv. Okay, so it's called read.csv. Now you tell me what's the input. What's the input for read.csv? The name of the file. That's it, which is called real state. So you can just put like RE and then press tab, and it will autocomplete the name of the file. Okay, so even if you didn't change the name of the file and it's like Sacramento real estate transactions, just put SAC Sacramento and then press tab and it will do autocomplete. Okay. .csv. Are we done? Yes. That's it. That's it. This is the code. Read.csv. Now, what happens when it imports the data? Where is it going to go? Well, if I run this code, it's going to print it in the terminal. I don't want that to happen. I can assign it to a data frame. Let's call it real estate or my data, whatever. And then just run this guy. There we go. We're done. See? Real estate is a data frame that has 985 rows and 12 columns. Remember we were talking about data frames last week? I told you when we import data sets, they will be automatically stored into a data frame. So this is a data frame. This is a data frame here that includes almost 1,000 rows and also 12 columns. Let's, I mean, like, I didn't have Excel installed. I don't have Excel installed on my Mac, so I couldn't really open it, but I can import it in R and then just click on it here and view the data set, right? You can view the whole data set. And just by looking at the column names, you can kind of, so again, does everyone know how to view the data set? All you have to do is just click on the name of the file here, name of the data frame here, right? I just click on this guy. I clicked on it, and it opens a new tab called Real Estate, which is the name of the data set. And then you can scroll down, you can scroll and see all the columns, right? Or the function is view that data frame with a capital V. By the way, every programming language is case sensitive. So it means so all of the functions, all of the variables, the data frames, the vectors are going to be case sensitive. So if you have like so view with capital V is different from V with small v. I mean, if you do it with small v, it's going to give you an error. All right. Was everyone able to load this into R?
No.
What is it? Are you getting an error?
I think it's path.
Oh, okay.
No
So.
such file or directory.
Oh yeah, exactly. So if you see this error, if you see like no such file or no such path, it means that the path is not correct. Okay. So what I did here is I think it's easier because I'm not using path. So make sure that you under files you navigate to the directory, the folder that includes the real estate transactions, and then click on this guy here, more. See, look at this here, more, and then set as working directory. Once you do this, you can just use the name of the file instead of the whole path. Okay? See, I did this, and then I used realestates.csv instead of using the full path to the file. Right? Just makes life easier. All right? Yeah.
So is there a difference if you use the import data set option?
Good point. Good point. See? Here it is. Import data set. Instead of writing code like read.csv, some people want to avoid writing code, you can also use this tool. It's on the GUI. Import files. Import data set. The difference is, if you write code, you can always customize it. Right? You can custom. But if you use these like predefined functionalities here, you can't really customize everything. Right? So because, for example, we're going to do read.csv, and then there's like tons of parameters that you can plug into read.csv to do different stuff, which I'll talk about like 2 or 3 of the common ones. Again, not every single detail, but maybe 2 or 3 that we use a lot. Now, I'm going to explain this function. So let's try to learn also about some other parameters here. What is the column name here? I mean, where did the column? How did we get these column names?
It was there in the CSV file.
It was in the CSV file. In which row?
First row.
In the first row. So whenever you do read.csv, by default, the first row is going to be used as column names. How about if your spreadsheet has raw data from row 1? You want to skip row 1, right? I mean, you don't want the read.csv to use your first row as the column name. In that case, you can say what is it? Like header name, I think, or header, or is it call name? I think call.names is equal to false. I'm not sure myself. Let's try it out. Oops. No, I think it's header, right? Does anyone know? Yeah, it's header. See what happened? It's using the first row as, it's putting the first row as raw data. And just assigning the column name as v1, v2, all the way to v, whatever. Okay, so this is what I did in the code. I mean, one of the parameters that you can use here is called header. By default, header is going to be equal to true, which means it will pick the first row of your data set and put it as header names. But if for any reason you don't have header names in your first row, that could be possible, right? You have to set header equal to false. Otherwise, your raw data will go into the header names. Okay? It's not a very big deal, but you're going to see like some weird column names there. Yeah.
After you provide the downloads back, how do you link to that? I did the same, but I'm still getting the no such file.
No such file? Okay. See, what I did was I just clicked here on more. Did you do this? Set as working directory? Yeah, that's it. All right. So this is something that is useful. I'm going to remove this for now, or I can just put true, which is the default, because my first row is column names, right? See? My first row was column names here in this case. Something else that is used a lot is many times your data sets have some empty rows at the beginning, right? So you want to skip them. Let's say you have like 5 empty rows, and then you have your header names, and then the raw data. So you have to skip 5 rows, and then read.csv is going to use the next row, which is like row 6 as column names, and then the rest of your data is going to be raw data. And it's very simple. It's called skip. Oops, sorry. Skip equal to the number of rows that you want to skip. Let's say like 5. I want to skip 5, okay? See what happens. What happened? It ignored the first 5 rows, and it used row 6 as column names. Yeah.
I see my data set in the environment location, but it doesn't show up on the, if it doesn't show up on the...
No, not double click. You need to click on the name of the data frame here. Only this part. If you click on it,
I've done that.
it's not?
Yeah.
Okay.
I do see the 985 objects.
Okay, I think you need to, if it's not showing up, close RStudio and open it from again. Quit RStudio,
Okay.
Open it from the beginning, yeah. All right, any questions? Again, that's pretty much it. I mean, again, there's many details here for read.csv, but these 2 or 3 parameters are probably the main ones that we're going to be using many times, yeah.
So some of these are blanks in the data.
Oh, so that's another story, right? Yeah. Let's say we have some missing values in our data set, or NAs. That's the next step, right? That's the next step, which we need to clean our data sets. We have to clean our data sets. But this skip, this parameter, the skip parameter, is for the cases which you have like absolute empty rows, and you want to skip them. But if you have a row that has like 2 missing data points, you don't want to skip them. You just want to import it first and then clean your data later. So that's a different story, and we'll talk about cleaning data just after this. Anything else? Was everyone able to import a CSV? All right, cool. That's it. That's it. Wanted to learn. So yeah, this is pretty much it. Read.csv. Or for Excel, there's again multiple packages that you can use. One of them is called gdata. This is a recent developed package, okay? It's recent developed. The old one was called the readxl. But for some reason it was not working properly, so I just replaced it with gdata. I think this is a better package. And the function that you can use is read.xls. Okay? Instead of read.csv, it's just read.xls. Do we need any other parameters here in addition to the parameters that we used in read.csv? I'm pointing to it. Yeah, sheet. Because in Excel file we have multiple sheets, right? Or we have one sheet. So you need to put the sheet name in double quotes, or the sheet number. The sheet number, that's even easier. Like 1, if you put 1, it's the first sheet, 2, second, and so on and so forth. You can also try this out, okay? This is also useful because we have tons of data in Excel as well. All right?
So
Question?
Different variables. So there's an ASCII file and a different read for that. If it just
Yeah, I mean, you can look into this guy here. Yeah, in this tutorial you can find like all different packages, all different functions that are used for. But as I said, like usually CSV, I mean, at least in the past few years for myself, all of the data that I've used was either in CSV, Excel, or on a SQL database, or other types of database, and general databases. Okay, that's it. Or barely sometimes like XML, sometimes text files, but it's usually like CSV. That's why we wanted to go through the function itself. But if you have like a new type that you want to import and you've never done it before, you can simply find it here in this tutorial. Question?
So you said SQL, right?
Yeah.
So is it being, are we going to connect it or
Yes.
import it?
No. Well, you need to connect in order to post or publish data onto the database, or even if you want to extract data from a database, so you have to connect to the database, right?
Yeah.
So for example, for MySQL, there's a package called rMySQL, and there's a function called connect dot, I forgot what it is. You connect to the database, given the user and password. You can connect to the database, and then send queries to the database, pull out the data that you need. Or you can also create a table here in R, and then publish the data on the database. You can post it there. You can send it to the database as well.
So you can connect multiple tables from this.
Yes, that's definitely doable. Yes.
So
Again, for almost like any technology, any database, if you want to see what is the corresponding package library in R, just put an R at the beginning. Like rMySQL, R Selenium is used for web scraping, which we'll talk about on week 7. Question?
for like every database we have access to SQL or
Most of, at least the famous ones, yes. SQLite, MySQL, Oracle, yeah, many of them.
Do you have to pull all the data into memory on your computer, or can you leave it as a connection so that if you're working with a massive database?
Depends. I mean, and we'll talk about this later, okay? I don't want to get into this, but it really depends on the type of the models that you're using, for example, because some models require the whole data to be there to train the model, but some models you can extract like chunk by chunk from the data set and train iteratively. Okay, so it really depends. Okay, we will talk about, not maybe too much details about it later, but once we get into the different models and classification and regression, I'll talk about it a little. All right. Now the next part, which is painful, but we have to do it. We have to clean the data, right? Cleaning data sets. Because, as you pointed out, if we import the data and we have NAs or we have missing values, sometimes we have to remove them. Sometimes, not all the time. Okay, but usually we have to remove them somehow. Now, the two most common types of junk data that we have to remove is either NAs, so NA, and I'll show it to you what I mean by NA in a real data set. NA, or it's just like missing data like this. Okay, these are the two most common types of missing values that we're going to be dealing with. There's a built-in data set, and I think it's called, I don't have it in the slides here, I think it's called air quality. So let's call it my data. I want to pull it up. Equal to air quality. There we go. If I run this guy, my data, look at it. See, like row number 5. You can see like 2 NAs, right? So this is what NA means. I mean, when you view the data set, you can see NA. And double quotes means an empty cell, which means like, just imagine like this was not here. This would be just an empty cell, right? So these are the two common types of missing values. Either completely missing or NA. And many of the functions that we use in R, or even other programming languages, cannot deal with NAs. That's why we have to remove them. For example, in prediction, later we will see. Let's say, for example, let's say we want to predict ozone from the rest of the columns. Okay? There's one of the columns that is missing here. So this means that we need to remove this whole row. I mean, this is not going to be informative because we have to use all these 4 or 5 features. Again, we'll talk about this in prediction. I think right now it's too early to get into this. But in general, many of the functions, or for example, tonight we're going to talk about correlation and some correlation analysis. And you will see the function for doing correlation in R is called COR, core, that's it. If you have NA and your 2 variables that you're measuring the correlation between them, it will give you an error. It will tell you that you have NAs. So you have to remove NAs, right? Or you have to set a parameter that will automatically do that for you. But anyway, so for removing NAs, there's 2 functions you can use. And this one is the easiest that I put in the slides. It's called complete.cases. If you apply complete.cases into a data frame like my data, the output is going to be the row indexes which are complete, which do not have any NAs in them. Example. Let's do it. Let's do it here. For my data, right? This guy. I'm going to run complete.cases. See, it shows up. And apply it to my data. See, it's giving me a bunch of true and falses. Let's look at from the beginning. This is telling me that row 1 is complete. Row 2 is complete. Row 3 is complete. Row 4 is complete, but row 5 and 6 is not complete because they have NAs. So even if there's like 1 NA in that row, it means it's not complete, right? So anyway, if you plug in, so I'm gonna write here, like let's clean the air quality data set, or in other words, let's remove the rows which have NAs. All right. All you have to do is create a new data frame. Let's say my data clean equal to my data, and then what? I'm going to put complete.cases in where? As the first input for my data, right? Because it's returning the row indexes. So I'm going to put complete.cases of my data. And once I run this, what happened here? What is my data clean? It has, as you can see, it has like 42 rows less than my data. Because we had 42 rows that had at least 1 NA in those rows. And we just got rid of it. So again, complete.cases is very useful. I mean, it's very easy to use. There's also another function called is.na. Simple to this one. But is.na, you need to apply it to every column by column and get like true and falses. So it's more complicated if you want to use it. You have to need a whole loop to iterate over it. But complete.cases will automatically look into all of the rows of your data set, and tell you which rows are complete. Yeah. Oh, so this comma means, remember, in order to access the elements in a data frame, we need 2 indexes, row index and column index. Once, if you put a comma and then leave it blank, this means all of the columns, right? Remember? So this means all of the columns, but only these rows. Only these rows. So that's why if you see in my clean data, the number of columns didn't change because we're picking all the columns. But only the number of rows changes because we're only selecting the rows that are complete, do not have NAs. Again, I mean, this is something you're going to be dealing with in the lab work and also in your final projects a lot. And as I said, it's very useful because there's NAs everywhere. All right, just need to go. I have to move a little faster.
If you're able to predict certain columns, right, certain data with a very accurate model, is that mean that could you then use that to sort of fill in some of these missing data?
That's a good point. Yes, that's possible. But we usually don't do that. I mean, because it's not very common. But yes, that's possible. Yeah. But you know, because sometimes it's like the missing data is not always one column. You know, it could be like from multiple columns. When you look alongside the whole data set, if you just accumulate them together, you will see like, oh, all of the columns have at least one missing data, right? Anyway, so the other type of missing data is, as I said, it's like blank data or blank cells. Okay. For removing these guys, you may find some packages and some functions for doing that automatically similar to this. I haven't found any. Okay, but what I do is I just like use which to point out. So everyone used which, right, in their lab work, because which is a very, very useful function. We use this a lot. And anytime you want to extract information out of your data set, you will definitely use which. Okay? So you put it like a bunch of, so you're going to say like minus remove the rows from this column which are blank. Okay, so we need a column number here. You have to put a column number. It should be a number. I mean, so obviously, if you want to apply this to all of the columns, you have to put it in a loop to iterate from column 1 all the way to column n for doing this. Okay. Again, you can try this out. You can try this out. It's one of the applications of which again. So one more time. In my data, we are removing the rows which, in my data, for one particular column, that row is blank.
What's the last column number?
Oh, very good point. So yeah, this part is just going to return the row number, and then in this column number, okay, the same column number that we're looking at here. So we have to do this column by column, as I said. So in one column or in one vector, you can see like which of the rows or which of the elements is blank. And then you have to do this over all the column numbers. So let's say the column number here is a fixed number. It's a constant. It's some given number.
So it removes the whole row?
It removes the whole row, yes. Yes, yes.
So is it just another way to do the complete?
No. This is different from NA. Like, so for NA, you see NA in the data set. But for this, you see like nothing. It's just like a blank cell, like nothing in it. But it's usually NAs. I mean, usually if there's missing data, it's usually NAs. Or you can also do something else. I mean, I would really recommend this. You can replace all the missing values with NAs. Again, using which. You can do that. And then apply complete analysis. This is easier. I'll probably put this in the slides for next time.
So
Because dealing with this is, I know it's not very straightforward. It's not very straightforward. Unless you write the code yourself and run it and see the results. Okay? Yeah?
So NA is like a package. Built-in
No,
package.
it's
We should
a-
remove the NA.
We should remove it, yeah. We should
No.
remove it. What?
I guess to remove the NAs, there's a built-in package for removing blanks if you write code.
Not a package, no. I mean, complete dot cases is the function that we use for removing NAs. That's it. There may be some other functions and packages. Complete dot cases is going to do the job for us. I know you'd probably be wondering why are we removing the rows that have NAs and not the columns that have NAs, right? You will see. You will see in prediction. In modeling, you will see that the rows are the instances. And if one instance has an NA, it's out. We can't use it because it doesn't have one of the features, right? So we have to look into other instances.
So
One more question, and then yeah.
when you describe NA, is it all like? Is it a keyword or like if uppercase, full uppercase, or
I know.
lowercase, and slash a?
Here it is. See, you see it. You see it. You see the actual NA. Even when you import CSVs into your data set, sometimes you see NAs. You see NAs.
Well, but the data set can have like some data sets may have capital N, capital A as NA. Some data sets have capital N slash capital A as NA.
Well, no, the standard format for NA and R is just like NA.
Okay.
All right. I agree. This is the most boring part of data analysis. But anyway, You can also look into these. This is an introduction to data cleaning with R. It's a pretty small book, 400 pages, I guess, and you can look into it. Again, it explains about, I mean, that's why, I mean, data cleaning is not like a very straightforward, simple process, okay? There's, as I said, tons of packages, like DPLYR, I just remembered, is one of them you can use with tons of packages, tons of tools. It really depends on what you want to do, and also the, but I mean, the most common thing that we want to take out of the data set, as I said, is just NAs and missing values. Also, some useful packages for data manipulation you can find here. As I said, like DPLYR is one of the most famous ones. DPLYR. All right, let's get into correlation analysis. What is correlation? Here it is. Co meaning together, relation. So if two sets are strongly linked together, we say that they have high correlation. Otherwise, they don't have a high correlation. Okay? And or in stats, dependence or association in any statistical relationship, whether casual or not, between two random variables or two sets of data. Is again a formal I'm going to start with a simple example. Let's say we have this data set, ambient temperature and ice cream sales. So we have two columns, two variables, right? Two random variables in this data set. The first column is the temperature in Celsius, and also the second one is ice cream sales. Do you think that there's any relationship or any correlation between the temperature, the ambient temperature, and ice cream sales? Yes, and we can figure this out by plotting, by doing the plot, right? So if you do a plot, temperature, if you do a scatter plot, temperature versus ice cream sales, you will see a linear correlation between temperature and ice cream. So this means that when the temperature increases, the ice cream sales also increase. Now, is this always valid? Is this always going to happen? No. If it gets too hot, people cannot come out of their houses to buy ice cream, right? So you can see the ice cream sales falls down. All right? Now, so given this data, if we do a scatter plot and we get this, we can say, okay, there's a strong correlation between temperature and ice cream sales based on this data. But someone's going to ask, is there always a strong linear correlation between temperature and ice cream sales? We're going to say no, because we found some more data points here that do not have that correlation. Now, talking about correlation, we want to quantify the correlation score. So that's why we just need some numbers here. And we define it as R. We call it R, the correlation score, which is the covariance of two variables, like the ambient temperature and the ice cream sales, dividing by the standard deviation of X times the standard deviation of Y. Okay, that's going to give us a score. And the score is going to be between -1 and +1. Okay, and then we're going to interpret it here. Or, I mean, if you just expand the covariance and the standard deviation, you'll get this. All right? I mean, obviously, we don't want to do this manually in R. Given the X and Y, we don't want to calculate this manually or do this in a calculator for sure. We're going to be using a function called COR. So this guy will do all the calculation. This guy. All right. Now, so what does the correlation score mean? If it's closer to 1, or if it's exactly 1, it means it's a perfect positive correlation. If it's closer to 0, it means there's no correlation, or almost no correlation. And if it's -1, there's a perfect negative correlation. Examples. Like this guy has a correlation of 1, exactly 1, because we can define a line, right? We can find a line that fits all the data points, right? Once that happens, it means that the correlation is exactly 1. And if the slope of the line is positive, it means the correlation score is positive. Okay?
But what if we go back to the ice cream example where it is almost perfect +1 and then it's almost positive?
Exactly. So this is like, let's say, correct. This is like 0.9, let's say, for example. But in that case, it's almost 0.
No, yeah, but
or it's like 0.1. So when we talk about correlation in stats, we mean linear correlation. Okay? Not just any correlation, because here you can see like temperature and ice cream is somehow correlated, but not linearly. Okay, so in stats, by default, everyone means linear correlation. And I mean, this definition is also based on the linear correlation here. And the scores that you get is again based on that. So you just have to see if you can fit a linear line or not. That's it. Now, the line that you fit, if it has a positive slope, it means the correlation is positive. If it has a negative slope, like this guy here, it's what? It's negative. Okay? Or in other words, in positive correlation, if one variable increases, the other one also increases. But in negative correlation, if one of the variable increases, the other variable decreases. Right? That's also another way to understand what is positive, what is negative. As you can see here, this is +1. This never happens in real life. In real data sets, you will never get exactly +1. Okay? If someone tells you you have a correlation of +1, they're lying. Or like this one is close to 1. As you can see, you can fit a line, but not all the data points are going to fall in that line. But it's again positive. And here it's getting close to 0. Finally, this is 0 correlation. This is almost, you can like fit a line like this. The slope is negative, so it's -0.3. And finally, this is a better one. So it's a stronger correlation, but it's negative. It's going to be -0.8. And finally, -1. Again, this is another way to define positive and negative correlation. If one goes up, the other one goes up. But for negative correlation, if one goes up, the other one goes down. All right, any questions? I'm going a little faster because I think it's probably straightforward. Maybe, I don't know. All right. Now, this is very important. Is the correlation score a good indicator of correlation? The answer is a no. No. Why? Because look at all these 4 plots. Okay? All these 4 plots are going to give you the correlation score of 0.8. But the correlations are very different. Like in this guy, only because of this single outlier, the correlation is not 1. And it's 0.8. Right? Or in this case, only because of this outlier, the correlation is 0.8. Otherwise, the correlation would be 0. Right? See? I mean, if you take this out, this could be an outlier, right? Just take it out. Okay, what line can you find that fits from here, right? What line can you find that fits here? Nothing, right? It's only just one data point is going to fit that. So it means correlation is almost 0 if you take that out. So again, okay, what is the best tool for analyzing correlation and understanding correlation? If it's not correlation score, so what is it? Look at it, exactly. Visualization, plots, scatter plot. That's the best way. Very easy. Okay, so correlation score, and honestly, it's very distracting. I mean, correlation scores are very distracting because a lot of times you have like very large data sets, which you cannot even open it in Excel or something, but you load it in R or some other tools, and you just do the measurement. So you want to do the correlation measurement without opening the file, right? And you get like 0.9 correlation, you say, wow, what a beautiful correlation I have here. But if you do the plot, you may see that, oh, just because of like one outlier, you're getting a very good correlation. Alright? Okay, so number 1 is visualization. But how about if visualization is not possible? It could be the case. If you have like 100 million data points, it's very hard to do a scatter plot on your own machine, right? It's probably going to take like 24 hours to get the plot. So what should we do then? Well, you can write a script to automatically remove the outliers. Remember, we talked about the definition of outlier in box plots? Like you can say whatever is out of the range of mean plus minus 2 standard deviation, just take it out, and then measure correlation. Okay, now that's more reliable. That's more reliable because you know you don't have outliers anymore. You don't have but still, the first method that we're always going to try to use is visualization for understanding correlations. This is also a very important question, kind of controversial sometimes. Is correlation the same as causation? If 2 variables have very high correlation, does it mean that they're causing each other necessarily? No. Why? Because there's tons of counterexamples. Like, number of people who drowned by falling into a pool correlates very well with films Nicolas Cage appeared in. Or per capita cheese consumption correlates with the number of people who died by becoming tangled in the bed sheets. Age of Mesoamerica correlates with murders by steam, hot vapors, and hot objects. Well, that could be true. Per capita consumption of mozzarella cheese correlates with civil engineering doctorates awarded. I mean, you can see like they both go up and down. That's what we mean by correlation here, right? Once one of them goes down, the other one also goes down. And then they go up together, almost, right? It's not perfect correlation, but they kind of correlate, right? So what is it? People who drowned after falling out of a fishing boat correlates with marriage rate in Kentucky. U.S. crude oil imports from Norway correlates with drivers killed in collision with railway train. Number of people who drowned while in a swimming pool correlates with power generated by U.S. nuclear power plants. That's it. So the answer is no. All right, any questions? Any questions about correlation score? We can also do some examples, like for correlation. Let me do one quick example. Since we have the air quality data set loaded here, go ahead and just do some correlation measurements here, for example. So I'm going to go back to my code here. I'm going to measure core, C-O-R. All right, what is the, like, what column should we look into? Let's see the data set, my data. Like, let's see if there's any correlation between ozone and solar radiation. Okay? Let's do this. So, what is the name of the data? I'm going to use, if you use my data, you will get an error because we have NAs. Okay, let's do it so you can see it. My data dollar ozone, comma, my data dollar solar radiation, and then run. See, the answer is NA because we have NA in the data. You can fix this with two solutions. First solution was just use complete.cases to remove the rows that have NAs, right? So we can easily just replace my data with my data clean. Or this is something else that could be useful. Add a third parameter, say complete dot.obs or objects, and then you will get a 0.34 correlation. See, that's how it works. I mean, this parameter here, use equals complete.object, is just like the same thing as applying complete.cases to the data set and then measuring correlation. It's just going to do it automatically for you. All right, and again, like just by looking at, so 0.34 is it's a low score. But again, this doesn't necessarily mean that the correlation is low because we may have outliers. If you do the plot, the scatter plot between ozone and solar radiation, there's some chance that you will see that, oh, there's a very good correlation, but just because of one outlier, it was ruining the correlation score. That could be possible. We can also do the ggplot, but it's going to take time, right? It's going to take at least 2 minutes. Any questions about correlation? Plots, correlation score, NAs? Everyone good? If anytime I'm going fast, stop me. Or if I'm going slow, let me know. Okay? I can go faster if you want. Yeah.
So basically, when I take core in this, like,
Yeah.
what it's doing is running the component in the back that you have outside.
Exactly. It's measuring the correlation between those two columns. And those two columns are X and Y in the formula that you saw. The covariance of X and Y divided by the standard deviation of X times standard deviation of Y. Sure, of course. The correlation you mean? Here. Sure. The example. Oh, you mean my code, right? This one?
Yes.
All right. All right. Any questions about? Yeah.
The point we will use. Now if I want to, so we, like how you expressed earlier, that just looking at the number is not sufficient.
Correct.
To visually interpret
Yeah.
it.
You cannot judge correlation based on number. Yes.
Then for that I need to use the
Scatter
number
plot.
apart from
Yes.
class
Exactly.
to the ggplot.
Exactly. Yes, that's a valid point. All right. So next part of the class is going to be a very, very exciting topic. Okay. I mean, it's my personal idea, honestly. Okay, I love that the topic, and it's called time series analysis. Time series analysis. The reason is because there's many applications, especially in healthcare, and you will see like remember the malaria project? Again, was based on time series data and how that project could save lives. So the same thing in time series. I think there's many applications, and especially in healthcare, which I'm going to talk about soon. We're going to spend maybe like 10 minutes on this topic. I wish we could spend more time on time series, as I said, because it's a very useful topic. And I would consider this topic like a more advanced topic. So after you finish this course, maybe one of the topics that you can touch and dig into more details is time series analysis after this course. Like once we get into like prediction, regression, and classification, you can apply the same concept to time series, but different models, different algorithms. It's going to be different. Like in discrete prediction, we're just going to predict one data point. In time series, you have to predict multiple data points because it's a time series. It's continuous data, right? Like in the stock market, if you build a model that predicts only like one data point, one price, does that really help? No. But if you can predict the trend or the time series for the next like week, well, you'll become a billionaire in 1 week, right? All right, real world applications. I also added some updates just this week. Time series analysis. Sensor data. I always forget to fix this missing S here. I don't know why. But anyway, sensor data is a gold mine. This project it's a real project I learned some time ago. A local restaurant in Amsterdam wanted to use big data analysis to increase the revenue. And they simply just used an EMF sensor, which stands for electromagnetic field sensor, that is able to detect a cell phone, right? You can buy this sensor from Amazon for like 15 bucks maybe. It's a very cheap sensor. And this is like the most fanciest one. Even simpler ones are like 4 or 5 bucks. And they installed one of these sensors in front of their stores to count the number of people that are crossing by the store. Because I mean, we can assume that almost everyone has a cell phone in their pocket, right? So if we detect the number of cell phones, it means we're kind of counting the number of people. And because this is a very simple sensor, that's why it's going to be very effective and cheap. And after they collected data, they did a plot over time and figured out that around like 10 o'clock every night, 10 p.m., there's like a peak of people crossing by the store. The reason was because there was a pub next door and people were just going to the pub, right? And this local restaurant was closing at 7 p.m. All they did was they expanded their working hours until 10 p.m. or 11 p.m. And the revenue doubled in 1 year. And the whole cost was one sensor.
And the salary for people to work extra hours.
Exactly, yes. Well, of course. I mean, I think everything included was it was like doubled. I mean, the whole like profit was doubled. I think this is going to be a cool job, right? If we become jobless, we can go and install these sensors everywhere and sell the data and information to different businesses. I'm really thinking about it, honestly. All right, I think we talked about time series data, right? Time series data is a lot of examples like EKG. Everyone remembers, right? Time series data, continuous data, or any type of data set that you have timestamps on the x-axis. The time series, as I said, they call it the real new big data because the type of data that you get from sensors is mainly time series data. That's the main reason, number one. Because we're getting sensors everywhere. We're getting sensors everywhere. On all our cars, our smartphones, everywhere. And the type of data that you collect from these sensors is usually time series. So these are like some applications. Not only that, for solving many problems in data mining, people transform their data into time series to solve their problem. And use some, the algorithms, existing algorithms in time series. For example, there are some functions, some packages you can use for transforming a video into time series. So instead of finding repeating patterns in the video, you can find repeating patterns in the time series. It's way easier. I mean, dealing with time series is easier than dealing with images or video, right? Or for example, you can transform the skull. If you want the paper for this, I can send it to you. It's a very nice one. It transforms every skull image into a time series and uses the time series to classify the type of the skull with a 90-something% accuracy. It's very cool. Or for example, there's an algorithm called MFCC. It's the most common algorithm used for transforming audio files into multiple or 13 dimensions of time series data. Handwriting. How can you get time series from handwriting? There are some products in the market available called smart pens. They have accelerometers on one end of the pen. So once you write down a word, you can collect the accelerometer data, and using that accelerometer data, you can detect what word the user is writing down or what letter they're writing down. It's a classification problem. I saw a very cool project done by some guy from MIT that he was actually doing this to understand like the whole sentence and all the words that the user is writing down, and then he had like a chip inside. He would detect the whole sentence, and he was saying that this is useful for like exams, final exams. You can just write the question. The question will be detected automatically when it's searched on Google, and it will tell you the answer. Right? Well, that was more like a joke, but it could be. It's doable. It's possible. It's possible. I mean, this data set exists. You can use this data set and build a classifier with very accurate results. Why is time series data a complicated topic? You can see why. We have like mess of data here. What should we do with it? I just been looking at the mess of time series data. It's like we don't really see numbers. We don't see any like meaningful pattern here. I mean, by eye, right? It's very hard to analyze time series data. The three main algorithms that the community applies to time series data are these three. Number one is called motif discovery, which means finding the most repeating patterns in time series. There's a famous algorithm for this one called MK, and it's probably the fastest. So you can like plug in any time series you want to MK algorithm, and it will give you the most repeating patterns, and it will sort them based on some scoring function. Number two, rule discovery. So rule discovery means at the end of this section for time series analysis, we'll see this. By the way, do you want to take a break, maybe, or not? Maybe not, right? Okay, because we only have like 20, 25 minutes. But I'm sorry, totally forgot. But again, if anyone wants to leave the class, take the restroom, feel free, anytime during class. So rule discovery means finding rules, predictions, in time series data. So if some pattern is observed, the model can predict another pattern coming after. Okay? We'll see some examples. Anomaly detection. Again, this is not only in time series, but the algorithm is different in time series. Okay? It means finding anomalies in your data set, which is again very, very useful. Talking about ECG, like a baby in a PICU at Children's Hospital is producing 12 time series possibly for weeks. So ECG is a great example of time series data. And there's a lot of ECG data there that people are not looking at it. But they could be useful. They could be very useful, especially for health monitoring stuff. So ECG is one of those examples. As I said, a project we actually worked on some time ago was using patients' ECG to predict a heart attack. I mean, this is real. So for example, if some sort of pattern is observed in your EKG or ECG, the model would tell you that, oh, you're gonna get a heart attack next week, for example. So just imagine in the future, on your smartwatches, you're gonna get a notification and telling you that, oh, you're gonna get a heart attack in the next hour. And you will get a heart attack right away. Right? But, I mean, we can maybe like send a notification to your cardiologist. And that's definitely possible. You can take care of that as well. But these are some stuff that is going on. Has anyone heard about this, CardiolifCore? This is a startup company in San Francisco. I think they have like 300 people right now. They have built this portable EKG sensor that connects through Bluetooth to smartphone and smartwatch, and also on the wristband of Apple Watch, you can find it there. This sensor is like $99 if you want to buy it, and I think I was the only customer maybe. It's pretty cool. I mean, the idea is very cool right now, that you just put your fingers on the sensor, two of your fingers, you put it on like both sensors, and you record your EKG for 30 seconds, and it will analyze the patterns of your EKG and tell you if it's normal or not. And then all this data is going to be stored on your cloud account. So that means that your cardiologist can log in anytime and look at the patterns, make sure everything is going right. So this is going to be very cool for, for people who have like heart diseases or heart issues. They can just monitor everything at their home. And this guy, Apple Watch Series 4, right? Who's going to buy this anymore, right? And Cardia, it's not going to be used. I mean, I just wasted my $100 here. But right now it's here on the crown, right? I mean, you can just put your one finger on the crown and record your EKG, and it's going to do the same thing again. And on the health app, you can see like if you have any issues, where like this guy is saying that everything is normal. There's no signs of any cardiovascular disease or anything. This is the future of health. I mean, I think it's kind of obvious that we're going to be having these wearable devices, and which have a lot of these built-in sensors. For example, there was like a heart rate sensor from an Apple Watch, the first series, like 3-4 years ago, right? It's different from EKG, but right now we have also ECG in it. And it means that our health is going to be monitored like 24/7, right? We don't need to go to the doctor anymore, right? It's going to be a very easy life. And you can also find like tons of stories about like how Apple Watch saved lives. People noticed, so if you get a very heart rate on your watch, you will get a notification and tell you that there's like something going on. And some people that got these notifications, they visited their doctor, and they were diagnosed with some cardiovascular problem, and they had to go under surgery, and their life was saved. Even a lot of young people, that happens. Talking about rule discovery, remember I said it's one of the very important applications in time series. And so this means that, I mean, we're talking about short-term prediction. It means that it would be really cool if an intelligent system would be able to predict just like 1 or a few milliseconds ahead of time. For example, if a robot would be able to predict that it's going to fall down like in 2 milliseconds, it can prevent that fall, right? I mean, if it knows that, if it has that knowledge. Or for example, robots that help other people to walk, if they notice, if they use some like machine learning model to predict that this guy is falling down, well, they can prevent that fall, right? Or for example, cars. This is something very neat and cool. If cars can use their sensors and cameras and using these machine learning models, if they can use it to predict a accident, a crash ahead of time, just like 2 milliseconds, it means that they can save lives, right? They can open the airbag ahead of time, they can press the brake, they can do a lot of stuff. This is something that Tesla is claiming that they're doing, actually. They have some radars under the car, also some cameras, and they can monitor like 4 cars ahead. And if there's like something happening, they will give you a warning. This is a real video recorded from inside a Tesla. You will see the car driving, and you will hear the beep before the accident happens.
How does Apple do that?
How does who?
Apple with the car.
We can talk about it later. All right. I think let's see if there's any. Oh, we can't hear it. Oh, yeah. Did you hear the beep? Yeah. Well, there was, I think, too much delay between the, and it's not like, it can't really predict like 5 seconds ahead of time. It's just like a few milliseconds ahead of time. But anyway, this is real. It's happening right now. It's there. Now, so there's an algorithm in time series analysis for discovering rules. I put the link here, the paper. It's open access if you want to see the paper. So this is the algorithm that is able to automatically detect meaningful rules in time series data. And it's not really important like what kind of domain it is or what type of data you have. As long as it's time series, plug it into the model, and the model will give you meaningful predictions. Now I'll give you some examples, okay? So I'm going to skip the details of the paper. If you want to look at it, it's a 10-page paper that includes all the algorithms and all the details there. These are some of the examples for demonstration purposes that show that this algorithm is able and capable of finding those meaningful patterns automatically. One of the data sets we used was called the leafhopper data set. It's a public data set you can use. So leafhoppers, sit on plants and suck sap from the leaves and cause, some damages to farms, right? For example, in Iowa, just one state, one type of leafhopper, the potato leafhopper, is causing $15 million of damage annually. And there's 30,000 species of leafhoppers in the US. Just imagine like how much damage they're causing to different farms. So scientists decided to do a simple study here. They wanted to collect some data, some time series data, from the different species of leafhoppers in order to study and analyze that data, to understand their species using that time series data, and also understand and analyze their behavior. Okay, and I'll show you how. All they did was they glued a wire to its head, which the leafhopper doesn't mind that much, and then once the leafhopper sits on a leaf and inserts the stylet, it's stylet into the leaf, that circuit there becomes activated, and then the change of voltage is going to give you a time series like this. Okay, and this time series is meaningful. Actually, I'll show you why. If you plug in that data into this model that I was talking about before, it will give you a set of rules like this. Okay, this is just like two of them. Okay, it's going to give you like a full list, and it will order them based on importance, based on some score, some MDL score. So this means the orange subsequence is called the antecedent. So if the antecedent is observed in your time series data, the green subsequence, which is called the consequence, is expected to be observed in the data. Okay, so in other words, if you see this pattern in your data, you can predict that happening. Okay. And
what's in the y-axis?
What's in the y-axis? Voltage, I think. Yeah, we got the data from here, right? This is the same data set. And so just by looking at this, we can't really say what is this antecedent? What kind of behavior is the leafhopper doing here? But we passed these patterns to an entomologist, which was familiar with this data set, and she told us that this antecedent is when the leafhopper starts inserting the stylet and sucking sap, and then this behavior is when the leafhopper starts shaking its tail to get rid of a drop of water from its tail. Okay. In other words, we can predict what the leafhopper is going to doing, right? Isn't that groundbreaking? So, the prediction here is maybe not very useful, but again, demonstration purposes. Okay? Again, you can simply show that this is working. Like I'm showing like two subsequences here that are matching each other, and finally you can see the consequence are also kind of matching almost, right? So it shows that this was a good prediction. It's not something random; it's meaningful. Can anyone hear this? All right, this is called a what? Zebrafinch. So, all right, anyway, so zebrafinch is this beautiful creature. It sings repetitively with a lot of repeating patterns. So we met a bunch of scientists in upstate New York that were studying these zebrafinches, and zebrafinches were actually learn how to sing from 40 days post-hatch to 100 days post-hatch. So during that 2 months, that's when their singing evolves. And these scientists were trying to change their singing patterns by playing some other sounds and and changing their patterns. Well, we picked one of these files, one of these audio files, before that 40-day, and we actually converted into time series using that algorithm that I mentioned, MFCC. And we picked one of the dimensions, we plugged it into the model, and the model came up with this rule saying that if this subsequence happens, this is going to happen, right? If this antecedent happens, that's going to also happen. I also put the audio file corresponding to each of these subsequences. I don't know if you can hear it or not, but if the zebrafinch sings this, something, then they will sing this, which you probably can't hear. So again, you can kind of predict what's going to happen. Again, we applied it on a different file, and the same thing happen. Okay, so in other words, this model, this intelligent model, can predict what a zebra finch is going to be singing. And finally, the last data set we used was energy disaggregation in a house. So there's a house with a bunch of tenants. We were monitoring the electricity consumption in the house for 2 years. For 2 years, okay? And all we did was we plugged it into the model and found this as the most meaningful rule or pattern. And because the data was labeled, which means at every timestamp we knew which home appliances were turned on and which were turned off. We figured out that this is when the clothes washer turns on, and this is when the clothes dryer turns on. So it means when the tenants turn on the clothes washer, after they're done, they will turn on the clothes dryer. Again, groundbreaking, right? Just for, again, this was all more for demonstration purposes. But again, if you have any questions, the code, all the data sets, the paper is all available on a website. You can, if you want it, just let me know. Or I also put a link to the paper. You can search it. Yeah, that's pretty much it. So as I said, I mean, there's many applications in time series data. If I just want to summarize this time series analysis, I think one of the most useful applications for time series data is health, number one. Number two, IoT. IoT devices, because as I said, all of these IoT devices have sensors, which the type of the data is usually time series data. That's why time series analysis has become a very, very hot topic. And it's also complex, it's very complex. For example, for building models and making prediction and classification, regression and classification, in discrete data, we have models built like 40 years ago. 40 years ago. I mean, the SVM model, neural network, these are very old models. Okay, they're not something new. People have been using it many years ago. But for time series data, it's very recent. I mean, this algorithm that I was talking about was like published 3 years ago. And before that, we don't have any accurate algorithm for predicting these meaningful rules out of time series data. So it's pretty, very important topic, time series data. All right. Finally, let's get into predictive modeling. We are going to spend some time on some introduction here, okay? And then for next week, you will get your hands on code, and we will actually, well, not me, you guys and Florence will write some code implementing models in R and using a package called Carrot to train models, test models, and see the results. So we're going to start with predictive modeling tonight, and we'll see some applications and some introduction for tonight. So first of all, why prediction is so important? It's really important because if you can predict the stock market, you can become a billionaire, right? Just by using that information. Or for example, in weather, this is something that we're using every day, right? Every time we're just looking at the forecast, see if we can go do something outdoor during the weekend. We're always using these machine learning models for weather forecasting. So it's in our everyday lives. Yeah, this guy used to be Trump. And the prediction, again, there's many applications, like in retail. The number one reason that Amazon is like beating everyone else, and like everyone else is going bankrupt, like Sears, Target, Walmart, they will soon become bankrupt as well, is because Amazon is using AI and machine learning technology in their company. That's it. That's the number one reason. I think on week 6 or 7, when we talk about association and learning, I'm going to talk about Amazon and some of the smart moves and some of the technologies that they have invented. Or like this Amazon Go store. I don't know if anyone has been there. They have it set up in Seattle. You've been there? Yeah. I went there, but it was only open to Amazon employees at that time. But I think recently they opened one. They're going to open one in San Francisco, I think soon. Which you go inside, take any items you want. There's no cashiers. You just run out, right? Just run away. And everything is going to get charged automatically, okay? And this is the future. I mean, it's obvious, right? The future of retail. People like it because AI machine learning brings convenience to our lives. And that's why all of us like it. So again, in retail, there's many applications of prediction, predicting prices, all that stuff. And also e-commerce, or for example, all of these recommender engines or recommendation-based engines, like in Amazon, once you pick an item, put it in your basket, it'll give you some recommendations, tell you that most of the customers who bought this item also bought this item, right? These are all based on these machine learning models. And that's how Amazon is pulling up all this information. Or like on Netflix, it always gives you some recommendations to watch the next movie. These are some other stuff that are, again, very interesting. Like the Doppler radar technology introduced in the last 2 decades that increased the mean lead time for tornado warnings from 5 minutes to 9 minutes. And that's like groundbreaking, right? I mean, just imagine like how many lives are going to be saved just by improving this prediction. Or predicting heart attacks from EKG, which we talked about tonight. Predicting the emergence of, this is very cool. If you have some time and you're interested, you can look into this paper. I put the link here. It's a paper published some time ago. I forgot what it was. Predicting the emergence of Alzheimer's disease in trial subjects well in advance at over 90% of accuracy using blood markers. Again, this is very, very cool stuff. Now, when we get into prediction, we have 2 types of prediction. Okay, let's make it very crystal clear. Number 1, regression. Number 2, classification. Okay? So we have 2 types of predictions. Classification and regression. All right, what is it? Regression means predicting numbers or continuous values. Or predicting numbers in general, right? I'll give you some examples. But classification means predicting categories or discrete categories. For example, see, this is regression. This is classification. Classifying a species, right? Because we only have, like, let's say 4 classes. So we're labeling every species based on one of these classes. This is called classification. Okay? So the definition of classification and regression is just like tied up to the variable that you are trying to predict. If the type of that variable is number, it's regression. It's a regression problem. If the type of that variable is categories, strings, labels, it's classification, right? Because you have classes, you have class labels. That's fine. Very simple. So some examples. For example, we need a regression model to predict, for example, predict stock values, or to predict future retail prices. See, we have numbers here. That's why this is regression. We're trying to predict numbers, predict the price numbers, the values, the demand for every item, for every merchandise. We need classification models to categorize bank loan applications as either safe or risky. What is it? Like, how many classes do we have in this problem? 2. It's a 2-class problem, right? Every instance is either going to be safe or risky. So it's a classification problem. Because you have classes, you have defined classes, categories. Categorize a spam email from a non-spam. We are going to do this in the class. We're going to download some real data from emails and build a classification model to determine if an email is spam or not. Okay? And even like one of the lab work is going to be applying this on your real email. Okay, we'll see it later. We're going to see this on week 6 and 7. Also categorize different species is another example of what? Classification. Exactly. Talking about predictive modeling, I thought of some project which we did for Bosch some time ago. Did you know that 60% of the revenue for Bosch comes from auto parts, not from washing machines or dishwashers or fridges? It's from auto parts. So a lot of German cars, they have Bosch auto parts in their engine. And so the whole project here was using some features to predict the demand for 30,000 different types of auto parts for the next 6 months. Is this classification or regression? Regression. Regression, because we're predicting the demand, we're predicting numbers, right? If we were going to predict like high or low, that would be classification, because you have like 2 classes of high and low. But here, it could be anything, it could be any number, right? So that's called regression. Just wanted to give you some example. Going back to the temperature, ambient temperature in the ice cream cells, problem. I just want to define the problem, but you'll see the code and also some regression analysis for next time, next week. So if you do this plot, you can see like that there's a pretty good linear correlation between temperature and sales. If you do this GG plot. Now the question is, are you able to predict the sales from the temperature? In other words, given the temperature, can you estimate the sales? Yes. Yes, that's it. This is building a regression model. So we want to build, given this data, given this information, I mean, we're starting with like the simplest regression model, which is linear regression model, and we will see it next time. But I mean, as we go further, we will see some more complex stuff, like random forest, neural network, SVM models, and blah, blah, blah. But like in this case, we can use a linear regression model to learn to estimate sales from temperature. So if we learn this line somehow using regression analysis, it means that in the future, given any temperature value, we can simply plot it and estimate the sales value, right? You can estimate the sales value. That's what regression is. So that's going to be it. So for next time, this is the goal. We want to find this. We want to find a linear regression model for estimating sales from temperature, which is going to be like the the best fitting line, and we'll talk about like how you can do that in theory. How can you calculate that line, find all the coefficients and the intercept of the line on paper, and also how you can do it with like 2 lines of code in R, using a package called Caret, the Caret package, which I'll talk about it in the lab work. Okay. We're finishing right on time. I'm impressed. All right, so the lab work for next time. Again, please spend time on it. If you have any questions, send me an email, okay? Or Google it, or send me an email anytime. Again, please review the slides. Download the real estate data set in slide 7, which we already did, and answer some of these questions. Answer these questions based on the Sacramento real estate transaction data set that we imported in the class, right? So number 3, how many unique cities exists in the city column? Do you know what function we have to use here? Unique. That's it. That's the function, right? Number 4, is there any correlation between square feet and price? There should be. There should be. All right. So go ahead and show the correlation, both numerical and also in a plot, in a scatter plot. Use a plot to show the distribution of the prices. You're going to use a histogram. So this is also some practice for ggplot, so that kind of refreshes the topic. Repeat task number 4 for price and latitude. Like, you'll see that there's no correlation probably. Is there any correlation between the number of beds and bath? Probably, yeah, there should be. Well, once you do these plots, you will see a lot of interesting stuff. Like you'll see outliers, blah, blah, blah. So please do this. Please spend some time doing this. I think you will learn a lot out of this. So, all right, compare the price ranges for different bed numbers. Which bed number has a higher price in general? Which bed number has a greater fluctuation in price? This is going to be what type of plot? Box plots, remember? We're going to have box plot, and we're going to have, because for different bed numbers, so it means bed numbers are going to be on the x-axis, right? 1, 2, all the way to like 5. And then on the y-axis, you can show a box plot for the price. And then you can simply compare the distributions of the prices for every bedroom, every bed number, every number of beds. Just one thing you need to keep in mind here, the number of beds is numerical. You need to categorize it using as the character, right? Because in this example, which we did before for the MPG dataset, remember, on the x-axis we had the classes of cars. So the classes of cars is automatically like categories. But for number of beds, it's numbers. So you need to apply as the character and then do the same thing we did before for MPG. Repeat task 8 for whatever. Find the rows which have only one bed. Or find the houses or the instances or the records in your data set that have only one bedroom. You're going to be using what function? Which. You're going to say which row number of bed is equal to 1. Find the rows which have a square feet less than 1,000 and at least 2 beds. This is why we need to use which, and not which.max or which.min, because which.max and which.min is just going to give you the max and min. But in general, you can use which to apply any conditions you want and get the right data that you need. Finally, please install the package called caret. It should be straightforward. I don't think you're going to get any errors. All you have to do is just go install packages, type in caret, C-A-R-E-T, caret package, and get it installed. Make sure you can load the library. All right, that's all for tonight. Thank you so much, and see you guys next week. If you have any questions, I'm going to be hanging around here. All right?
Do you post the lab works, or will you post it at the end of the class?
Some of them I will,
Okay.
but not all of them.
Not all.
Yeah, the reason is because